Hi, I'll be presenting our work, Affordances from Human Videos as a Versatile Representation for Robotics. In this project, we aim to enable robots to learn directly from watching unstructured videos of humans doing many tasks. We do this by learning visual affordances. To train our model, we extract contact points and trajectories from human videos. Let's see the affordance model in action. The robot is placed in an unseen kitchen. It first predicts different contact region and pick one. In this case, the handle of the drawer. It also predicts the post-interaction trajectory, shown here in green, and then executes the task. We're able to seamlessly deploy our affordance model in 4 prevalent robot learning paradigms and show that it can boost performance in all of these. Let's now dive into the approach. Firstly, we want robots that can operate in the wild. We want to see robots doing thousands of different tasks in thousands of different environments. But there exists no such data set to train robots. Maybe we can use data from the best robot that's already out there, ourselves. We can try to use the billions of internet videos of humans performing different tasks to help the robot learn some skills. However, there exist multiple challenges in learning from videos. Most importantly, a robot does not look like a human, it does not move like a human, since it has a completely different morphology. Secondly, we can't really tell anything about the physics of the world from a single video, like how an object feels or how much force to apply. Thus, is it possible to learn action information from diverse videos directly? The paradigm that we propose is to first watch humans, extract some behavior priors, and then improve and explore around these. So what are the right priors to extract from humans? This is a long-standing question that has been deeply studied in computer vision. So we take an inspiration from the seminal work in the field of affordance learning. Taking a step back, to execute any task, the robot needs to know the following: what object and where it should interact. This is important because it reduces the search space. It needs to know how to get to said interaction point. But kinematics are usually known, so we can rely on planning for this. Finally, it needs to know what to do after it has grasped the desired object, which is difficult. Thus, our formulation of affordances specifically focuses on the contact point and the post-contact trajectory. Concretely, let's see how our affordance model works. Let's take this video from the internet of a person opening a fridge door. Using a hand object detector, we first find the contact region. We then obtain the post-contact trajectory by tracking the wrist of the human after the initial interaction. However, these frames contain humans, and thus there is an embodiment gap. How can we learn in a human-agnostic manner? Our simple trick here is just to map the affordances back to the first frame without any human and use that to only train the model. This allows us to handle the domain shift much better. This model consists of a two-headed network predicting the contact heat map and the 2D post-contact trajectory, as you can see here. To deploy it in the real world, we simply take the image in front of the robot and then just run our model. The model predicts the contact point region and a distribution of trajectories the robot should take after it grasps the object. We convert the affordance into a 3D trajectory and use a low-level controller to execute it. In summary, we call our approach VRB, or Visual Affordance-Based Robot Learning. First, we can look at the quality of the predicted affordances. Here we show examples of VRB compared to state-of-the-art affordance learning methods on 8 different tasks. VRB in the top row predicts a very intuitive and usually correct affordance, as you can see here. Instead of finding a particular way to use our affordance model for robotics, we show that it can bootstrap existing robot learning methods. Specifically, we consider 4 common paradigms: imitation from offline data collection, goal conditioned learning, exploration, and redefining action spaces. Firstly, when performing imitation from data collection, obtaining human demonstrations is expensive, and collecting data using a random policy will yield very suboptimal datasets. On the other hand, executing affordances from our model, the robot has a much higher chance of getting interesting interactions and thus getting a much richer data set, as you can see in this time lapse of the offline data collection process. Even qualitatively, we see very meaningful interactions for all the tasks. Using these static datasets, we can perform imitation learning using standard algorithms. We performed extensive comparisons and experiments in the real world and found that VRB outperforms both random data collection, which is the norm in robotics, as well as other affordance models. How about the case where the robot already knows the goal it has to reach, like an image of an open cabinet door? Using our affordance model can expedite this process of solving goal-specified tasks. Instead of sampling random action, the robot simply samples actions from our affordance model. Here we show the time lapse of the goal condition learning experiment, and the goal image is on the top right. At first we see few successes, but over time it is able to open the dishwasher pretty well. Similarly, we have a garbage can opening task here. We can see high success rates just after 1 to 2 hours of interaction. For more details and numerical results, we encourage you to check out our paper. Starting exploration from scratch is too inefficient in the real world because the robot can spend a very long time trying to explore and still not learn anything meaningful. On the other hand, VRB can inform about the interesting interactions and show how to perform them. Here is the exploration time-lapse of the pot task. Similarly to the goal reaching, the agent samples actions from the affordance model and optimizes intrinsic rewards. Another big difficulty in deploying a robot in the real world is an exponentially large continuous action space. On the other hand, our affordance model can automatically generate interesting primitives which circumvent this problem. Thus, we discretize the output of the model, as shown on the right here. We then use DQN directly in the real world on 2 different tasks and find that the VRB action space makes solving the tasks much easier, seeing successes in just under 30 minutes. Here are some videos of VRB run on many different tasks in the wild. Thanks for watching this video, and for more information, we encourage you to check out our website, paper, and poster.